When you look at human anatomy, it's easy to underestimate the female breast. A common assumption is that it consists almost entirely of fat. But underneath the surface, it is a highly dynamic, modified apocrine gland, a living architecture that constantly remodels itself throughout a woman's life. To understand how it changes, we have to establish its physical baseline. There is zero muscle tissue inside the breast itself. Instead, it rests entirely on top of the Deeks fascia, the thin layer of connective tissue covering the pectoralis major muscle of the chest wall. What holds this tissue in place is a network called Cooper's ligaments. These act as the primary support system, anchoring the internal breast tissue both to the overlying skin and to the deep chest wall. These vertical, triangular bands of connective tissue are responsible for maintaining the physical shape of the breast. Over decades, these specific ligaments slowly lose their strength and tension, which alters the external contour. During childhood, the internal structures suspended by those ligaments are largely inactive. In this prepubertal stage, the breast consists mostly of structural fat pads and basic undeveloped ducts. It is a dormant architectural blueprint. The structure is already laid out, but it sits completely still, waiting for a specific chemical start code to begin construction. That start code arrives in early puberty, during a phase known as the larky. But the signal doesn't start in the chest. It begins as a top-down chemical command originating deep inside the brain. It works as a biological chain reaction. First, the hypothalamus triggers the pituitary gland to secrete specific regulatory hormones. These travel through the bloodstream and command the ovaries to start producing a massive wave of estrogen. When estrogen molecules reach the chest, they bind directly to receptors inside the breast cells. This binding initiates the expression of specific genes, which then release a surge of growth factors to build new tissue. This illustration highlights the result of cellular activation. We see the rapid formation of club-shaped terminal end buds. These group together to form terminal ductal lobular units. Zooming out, you see how these units form the breast functional core, branching through the fat. This pubertal construction shifts the breast from a dormant fat pad into a chemically sensitive organ, now fully wired into the body's endocrine system. Once puberty finishes, the adult breast enters its maintenance phase, but its internal structure never stays static. It is dictated by the continuous rising and falling rhythm of the monthly menstrual cycle. This table compares the specific localized effects driving this cycle. While estrogen drives the continuous growth of the ductal systems and the deposition of fat, progesterone handles the intricate work, forcing the budding of tiny new milk-producing sacs called alveoli. Because hormone levels fluctuate every month, the breast tissue is locked in a state of constant micro-remodeling. The internal lobules physically expand as hormones peak and then quietly regress as those levels drop off. If a pregnancy occurs, that monthly loop halts. The body begins flooding the system with sustained surges of hormones, pushing internal construction into overdrive. The tissue undergoes a process called lobular hyperplasia. The milk-producing cells multiply so rapidly that they completely crowd out the fibrous connective tissue that normally separates them. These histological slides show extreme physical contrast. The top inactive gland is mostly clear space. Below, the active gland is densely packed with swollen alveoli. Finally, prolactin stimulates milk production, while oxytocin contracts surrounding cells, squeezing fluid from the lobules down lactiferous ducts toward the nipple. With its massive cellular growth and coordinated fluid transport, this phase represents the peak of the breast's functional capacity, pushing its internal architecture to its absolute limit. Eventually, the rhythmic engine of the childbearing years reaches its final phase, menopause. Cyclic communication between the brain and ovaries finally begins to power down. The immediate chemical fallout is systemic. The circulating levels of estrogen and progesterone that rebuilt the breast tissue for decades drop dramatically and permanently. This diagram highlights the biological response, a process called involution. Without those hormonal signals, the breast's complex ductal systems shrink and the supportive stroma recedes. As the network retreats, the physical density of the breast changes. The complex glandular tissue of youth is systematically replaced by soft adipose fat. Because this cellular replacement isn't always uniform, it creates functional nodularity, the natural changes in texture and density that many women experience in later life. A woman's breast is a living biological timeline. It is a physical map documenting her entire endocrine history, capturing every fluctuation from the awakening of puberty to the quiet of menopause.